January 1943, over northern Germany. The sky is white with ice and smoke 20,000 feet above the earth. A formation of American B-17 flying fortresses pushes through the thin air, engines glowing red in the cold. Their contrails twist across the pale horizon like scars in the winter sky. Below, the ground flashes with bursts of flak, black clouds erupting around the bombers. Inside one of the lead aircraft, every vibration tells a story of strain. For Wright R-1820 engines thunder relentlessly, their propellers clawing at the frozen air. But what keeps them alive isn't brute power. It's something invisible, hidden deep within the metallic veins of each engine. A small turbine spinning faster than thought, feeding compressed air into cylinders gasping for oxygen at impossible altitudes. Without it, the bombers would stall, drift, and die above the clouds. With it, they rule the stratosphere. Few of the men aboard know the name of the man who made this possible. Fewer still know that his invention, once laughed out of army tests, would turn the tide of an air war. The idea that exhaust, waste energy pouring from an engine, could power flight, began not in a hangar, but in a quiet laboratory. It was 1918. The First World War was still burning across Europe when a young engineer named Dr. Sanford Alexander Moss at General Electric began to imagine what others dismissed as impossible. Capturing the heat of exhaust gases to drive a compressor, forcing denser air back into an engine. In those days, airplanes were frail machines, limited by the thinness of air at high altitude. Engines gasped for oxygen. Performance dropped sharply beyond 10,000 feet. Pilots learned to fight low because the sky above was, to their engines, a suffocating void. Moss, however, was an engine man. A thermodynamicist by training, he saw energy where others saw waste. If a turbine could spin fast enough, it could compress air before it entered the engine, restoring its power in the thin upper atmosphere. He called it the Turbosupercharger. General Electric gave him a small budget and a few machinists at its Lynn, Massachusetts plant. By the spring of 1918, he had built the first working prototype, a crude bronze contraption that looked more like a plumbing experiment than an aircraft component. It was tested on a Liberty V12 engine, mounted on a dynamometer. To the astonishment of observers, it worked. The engine delivered near sea-level horsepower at 15,000 feet of simulated altitude. The Army's Bureau of Aircraft Production took notice. A test was scheduled at Pikes Peak, Colorado, 14,000 feet above sea level, to prove whether Moss's device could sustain power where engines typically failed. The results were undeniable. His turbocharged Liberty engine achieved more than 80% of its ground-level power. It was, in 1918, a world first. Yet, the war ended before the idea could be used in combat. When peace came, America disarmed. Aircraft budgets were slashed. Aviation research withered under the belief that there would never be another war like the last one. For Moss, the dream didn't die, it went dormant. Throughout the 1920s, he continued refining the system, even as the Army Air Service turned away. They called it too complex, too heavy, too expensive. A machine for which there was no immediate need. The irony was bitter. Europe's air forces were advancing. Germany, under strict post-war limits, was quietly studying forced induction. Britain and France were experimenting with superchargers driven by gears. But the United States, with its vast skies and industrial promise, looked away. Still, in laboratories at General Electric, engineers continued their work. They improved turbine metals, experimented with heat-resistant alloys, and solved vibration problems that destroyed early prototypes. Dr. Moss retired in 1938, but his designs were left behind, blueprints waiting for a war that would demand them. When the clouds of conflict gathered again over Europe in 1939, the United States Army Air Corps faced a crisis of vision. They had the manpower, the factories, and the will to produce bombers that could reach deep into enemy territory, but they didn't yet have the engines to take them there. In those first uneasy years before Pearl Harbor, a handful of officers and engineers would reopen Moss's old files and realize that the rejected invention from 2 decades earlier might be the key to building a bomber that could fly higher and farther than any in history. The path to rediscovery, however, would not be smooth. By 1939, the world was once again on the edge of catastrophe. Hitler's armies had crossed into Poland, and the skies over Europe began to fill with the thunder of engines. In the United States, the Army Air Corps watched uneasily. Its aircraft, still slow, underpowered, and short-legged, would be no match for what the Germans were now flying. The American doctrine of air power was built on faith, the belief that strategic bombing could win wars. But that faith required a machine capable of reaching enemy factories and oil fields deep inside occupied Europe. It needed altitude, endurance, and reliability, the holy trinity of survival above hostile skies. And that meant a new kind of engine. At Wright Field, Ohio, test pilots and engineers were struggling with the limitations of mechanical superchargers. These were gear-driven compressors that stole power from the engine itself. They worked well at medium altitudes, but as aircraft climbed higher, the thin air turned their advantage into exhaustion. The engines overheated, sputtered, and died long before reaching the operational ceilings that strategists envisioned. The Wright Aeronautical Corporation and Pratt & Whitney both tried to push mechanical systems further, but the results were disappointing. At high altitude, where air density fell sharply, even the best superchargers choked. And that was when someone, searching through old reports, stumbled upon the forgotten work of Dr. Sanford Moss and his exhaust-driven turbosupercharger. The idea resurfaced quietly, almost accidentally. In 1938, a new bomber project, designated Model 299, had been proposed by Boeing. It would later become known as the B-17 Flying Fortress. Engineers knew that to carry a full bomb load at 25,000 feet, it would need power that no existing engine could deliver unaided. So they turned to General Electric. The old company, still proud of Moss's experimental legacy, agreed to revisit the turbosupercharger. They dusted off decades-old blueprints and began work at their plant in Schenectady, New York, under the guidance of a younger generation of engineers who revered Moss's early experiments. At first, the Air Corps was skeptical. Turbines operating at 20,000 revolutions per minute, exposed to 1,600 Fahrenheit exhaust, seemed too fragile for combat service. The system added weight, complexity, and maintenance demands. Commanders questioned whether it was worth the trouble. But flight tests told a different story. When the first prototype B-17 equipped with G turbosuperchargers lifted off, it climbed faster and higher than anything the Army had ever seen. At 25,000 feet, while other bombers lost half their power, the B-17's engines still roared with full strength. The effect was staggering. For the first time, heavy bombers could cruise well above flak bursts and interception altitudes. The dream of daylight precision bombing, once theoretical, became suddenly possible. Even so, the program nearly died several times. Funding cuts, technical failures, and bureaucratic rivalries haunted the project. Some officers still called the turbo Moss's folly. But after the fall of France in 1940, priorities changed overnight. The United States knew war was coming, and now altitude and range were survival itself. By 1941, with General Electric's turbocharger firmly integrated into the Wright R-1820 Cyclone engines, production of the B-17E began. It would soon be shipped across the Atlantic to Britain, where its high-altitude power would face its first true test against the Luftwaffe. That test would reveal what Moss had seen decades earlier. That waste energy, when properly harnessed, could become the weapon of the skies. In every great machine, there lies a trace of the people who refused to abandon it. The story of the turbosupercharger was not only about airflow and altitude, it was about stubbornness, failure, and faith in invisible forces. At the heart of it stood Dr. Sanford Moss, an unassuming man whose laboratory notebooks from the 1920s read more like the journals of a craftsman than a scientist. He wrote in neat lines about turbine blade fatigue, compressor efficiency, and the haunting problem of heat. He had retired before the B-17 ever took flight, yet his fingerprints were all over its heart. When General Electric revived his design in the late 1930s, a new generation of engineers took up his mantle. They were young, men in their 20s, fresh out of MIT and Cornell, and they faced the same doubts their mentor had faced decades earlier. Many Army officers thought the system too fragile for combat. Metals of the day warped under extreme heat. Bearings failed after minutes of sustained operation. A single crack in a turbine blade could spell disaster. So, in small workshops at Geeslin and Schenectady plants, engineers began a relentless cycle of trial and error. They built furnaces that could simulate exhaust temperatures, testing dozens of alloys, nickel, chromium, molybdenum, until they found one that could survive. They created new lubrication systems to prevent oil from burning inside the turbo's tiny bearings. They refined the compressor's impeller, balancing it to within 1/1000th of an inch. The men who worked on those early systems described the noise as a scream in metal. When a turbo failed on the test bench, it disintegrated like a grenade, shattering windows and sending shards across the floor. But when it worked, the sound changed. A deep, even whine, rising with perfect symmetry. That tone became the heartbeat of American heavy bombers. By 1941, General Electric's engineers had managed to shrink the entire assembly into a self-contained unit weighing just over 100 pounds. It could capture the scorching exhaust gases from the bomber's engines, spin a turbine at incredible speed, and drive a centrifugal compressor that forced compressed air back into the cylinders. The result? A seamless, altitude-compensating system that made the Wright Cyclone engine nearly immune to thin air. For the pilots, the effect was miraculous. A B-17 could now climb above 30,000 feet without gasping for power, could maintain formation where German fighters began to lose performance. In the cockpit, airmen didn't think about the physics, they only felt the difference. Engines no longer faded at high altitude. Throttle response stayed crisp. They could hear the soft, constant hum of the turbos working beneath the roar, a sound that meant survival. Few of those airmen ever knew the name Sanford Moss, or that his design had once been thrown out of Army reports as impractical. But his persistence had bridged the impossible, turning exhaust into lift, waste into dominance, and rejection into power. Above all, it had proven a simple truth of wartime invention, that sometimes the smallest unseen mechanism decides who commands the sky. Technology alone never wins wars. It must find its purpose in strategy. For the U.S. Army Air Forces, the turbosupercharger was not just an engineering marvel. It was the missing link between vision and reality, between the dream of precision daylight bombing and the brutality of modern air combat. In the late 1930s, both Britain and Germany had chosen a different path. The Royal Air Force, burned by early losses, turned toward night bombing, safety in darkness, trading accuracy for survival. The Luftwaffe, built for tactical support, relied on low-altitude attacks that demanded speed rather than endurance. Only the Americans still clung to the idea that bombers, flying high and tight in daylight, could strike industrial targets with scientific precision. It was a doctrine as bold as it was dangerous. But without the turbosupercharger, it would have been suicide. At 25,000 feet, the air is half as dense as it is at sea level. Engines without forced induction lose roughly 40% of their power. Mechanical superchargers could help, but only up to a point. Above 18,000 feet, their efficiency collapsed. Turbosupercharging, however, changed everything. Instead of drawing energy from the crankshaft, the turbo fed on exhaust energy, power that would otherwise vanish into the cold air. The higher the altitude, the more valuable that energy became. The engine's output remained stable, its performance curved flat where others plunged. This was revolutionary for bombers like the B-17 Flying Fortress and later the consolidated B-24 Liberator. American bomber crews learned to use altitude as both shield and sword. Flak batteries had limits. German 88s struggled to reach beyond certain heights. Fighter performance also declined sharply with thinner air. Their engines lacked the same turbo advantage. The Luftwaffe's Messerschmitt Bf 109s and Focke-Wulf 190s were formidable at medium level, but at 30,000 feet, their climb rate and maneuverability dropped. That thin layer of air became the fortress wall the Americans had imagined. In formations of 100 or more, the B-17s exploited this margin mercilessly. Their turbos kept them cruising above interception altitude, engines synchronized, their sound like an approaching storm. Each aircraft carried multiple machine guns, but its greatest defense was simply being unreachable and still powerful at those heights. German pilots were stunned. Reports from Luftwaffe commanders in 1942 described the shock of seeing bombers, still gaining speed where our fighters began to stall. The enemy could climb, but not long enough to engage. Fuel was spent, engines overheated, and the bombers continued on. Behind this tactical miracle lay something profoundly American, the fusion of industry and invention. Every turbocharger demanded the precision of a watch, yet it was built in the thousands by a nation turning out bombers by the hour. The system worked not only because Moss had imagined it, but because U.S. factories had learned to produce it at scale. By 1942, American bombers were not just flying high. They were flying beyond the limits of the Luftwaffe's reach. The Germans would soon answer with new weapons, new tactics, and desperation. But the sky itself had shifted. Altitude now belonged to the United States. And soon that advantage would be tested in the fires of Europe. The winter sky over Germany in 1943 was a frozen battlefield. From the ground, civilians could trace the war by the trails in the clouds, long white lines stretching east to west, marking the path of American bombers as they crossed into the heart of the Reich. By now, the 8th Air Force, based in England, had committed fully to the doctrine of daylight strategic bombing. Their aircraft of choice, the B-17 Flying Fortress, 4-engine, heavily armed, and powered by Wright R-1820-97 Cyclone engines fitted with General Electric turbosuperchargers. Every mission was a test of altitude, endurance, and belief. On August 17, 1943, that test reached its breaking point. Two massive bomber streams took off from England before dawn, one bound for Regensburg, the other for Schweinfurt, the twin beating hearts of German aircraft production. The operation was designed to cripple the enemy's fighter industry. But it also became the moment when the turbocharged bomber would prove its worth beyond theory. The plan called for bombers to fly unescorted across hundreds of miles of enemy territory, beyond the range of Allied fighters, relying on altitude and formation strength to survive. As the sun rose, the formations climbed through layers of ice and cloud, leveling off near 28,000 feet. Engines strained, air thinned, and frost formed on the wings. Below them, the German radar network began to pulse with activity. Soon, the sky filled with black smoke. Flak bursts timed to detonate precisely at altitude. The concussions rocked the formations, but the bombers pressed on, their turbocharged engines howling. Each Wright Cyclone, boosted by Moss's invention, maintained sea-level power despite the near-vacuum outside. The airmen trusted that steady roar. It meant the difference between control and chaos. Luftwaffe fighters, Bf-109s and Fw-190s, scrambled to intercept. But at those altitudes, their climb rates plummeted. Engines overheated, and some fighters stalled before they could even reach firing position. The few that did found themselves closing on bombers that still flew strong and straight at 28,000 feet. Germans on the ground watched in disbelief. The Great Silver Formations, nearly 200 aircraft, passed over their cities like an unstoppable tide. Despite the flak, despite the cold, the bombers didn't waver. To the Luftwaffe, it was a stunning display of power, not just of numbers but of endurance. When the bomb doors opened over Regensburg, the turbos still screamed with perfect rhythm. Engines that should have suffocated in the thin air instead pulled the massive aircraft through each turn and dive. Bombs fell on the Messerschmitt factories, crippling production lines that had supplied the German fighter arm. For the Americans, the cost was terrible. 60 bombers lost that day. But for those who survived, one truth was undeniable. At high altitude, they were kings. The Luftwaffe could attack them, but could not match their reach. And as the formations turned for home, the men inside those flying fortresses knew that their survival rested on something small and spinning, hidden deep in the exhaust stream, the rejected machine that had just rewritten the laws of the air. The Schweinfurt-Regensburg raid was only the beginning. In the months that followed, the air war over Europe became a contest of endurance. Altitude against attrition, innovation against desperation. For the Americans, every mission deeper into Germany was an act of faith in their machines. For the Germans, every climb into that thin, frozen sky was a fight against physics itself. The Luftwaffe quickly understood the threat. Their intelligence reports described the new American bombers as apparently immune to altitude. Engineers in Augsburg and Dessau began experimenting with high-altitude fuel mixtures and mechanical two-stage superchargers to give their fighters the strength to reach the bombers. But for every technical step forward, the Americans had already moved higher. The turbosupercharger changed not only the ceiling of flight, but the rhythm of battle. It allowed bomber formations to choose where the fight would happen, and more importantly, where it would not. The Luftwaffe's defensive belts of fighters and flak were designed for lower altitudes. Their effectiveness declined sharply above 25,000 feet. Now, the Americans could cross into Germany from the North Sea and emerge nearly untouched until the final approach to target. In October 1943, during the Second Schweinfurt raid, this new dynamic reached its peak. German ground observers watched as waves of B-17s appeared high above the contrail layer, specks of silver in a clear autumn sky. Flak bursts reached for them, but rarely found their mark. Fighters climbed, stalled, and fell away. From below, it seemed almost supernatural, these machines that carried tons of bombs at heights where birds could not breathe. Inside the bombers, however, it was no miracle. It was engineering. Pilots monitored turbo gauges constantly. A flicker in pressure could mean engine failure, and in that airless cold, failure meant death. But as long as the turbos spun, they carried life. Each engine's exhaust, hot and furious, fed the turbine, which in turn fed the engine again, an endless loop of mechanical resilience. After hours of flight, the bombers turned for home. Many were torn and smoking, yet their engines still held steady. Crews often returned with engines running at near sea-level output, even after losing oil, fuel, or cylinder pressure. The turbo's steady whine, constant and reassuring, became the sound of survival. The Luftwaffe would never fully overcome it. They built the Me-410, the Ju-88C, even experimented with rocket-assisted climbs. But they could not sustain altitude combat long enough to break the American formations. The Reich's aircraft industry, the very target of those raids, began to crumble under the weight of its own limitations. From the freezing altitudes above Germany, it became clear the United States had turned invisible energy into advantage. Exhaust became thrust. Waste became endurance. And at the center of it all was an idea once deemed unnecessary, now carving the future of aerial warfare into the thin air of Europe. The war, however, was far from over. Beyond the victories in the sky, the question remained, how far could American industry push this hidden power before the next great leap in flight? When the smoke cleared over Europe, the legacy of the turbosupercharger was written not in blueprints, but in the balance of the air war itself. By late 1944, the 8th Air Force was flying daily into the heart of Germany, Berlin, Merseburg, Dresden, Hamburg, cities once considered unreachable. The average cruising altitude had risen to over 25,000 feet, and the B-17's operational ceiling often stretched beyond 30,000. In those frozen altitudes, German defenses faltered. Anti-aircraft artillery, once a deadly curtain of fire, lost its precision as air density dropped. Shell fuses burned too long. Shrapnel spread too wide. Radar-guided predictors struggled to track targets so high and fast. What the Americans had achieved was not invulnerability, but inevitability. Each mission brought staggering losses, yet each mission also crippled Germany's industrial arteries. By early 1945, synthetic fuel plants, ball-bearing factories, and transport hubs were systematically dismantled from the air. The Luftwaffe, once feared across Europe, now faced its greatest enemy, exhaustion. Their fighter pilots climbed until their engines gasped, while the Americans soared higher still, engines singing with that distinct turbo howl. The device's impact rippled far beyond the bomber fleet. P-38 Lightnings, fitted with twin turbocharged Allisons, began sweeping the skies over Italy and southern France. The P-47 Thunderbolt, powered by the mighty Pratt & Whitney R-2800 with a GE turbo, became a high-altitude hammer, a fighter bomber that could climb above the weather, dive like a meteor, and return unscathed. And when the P-51 Mustang finally arrived with its British Rolls-Royce Merlin engine, the combination of efficient design and high-altitude performance completed the Allied air dominance. For the men inside these aircraft, the effect was personal. Veterans remembered the sound of the turbocharger as a metallic heart, pulsing with life even when every other system seemed to fail. At 30,000 feet, frost covered every surface, and oxygen masks iced over. Yet the turbo's steady hiss was proof that someone back home, a machinist in Ohio, an engineer in Lynn, a factory worker in Erie, had built something that would not give up. In technical reports filed after the war, General Electric's engineers noted the turbo's unexpected reliability. Despite brutal conditions, most failures were minor: clogged wastegates, frozen control lines, problems the crews learned to fix midair. It had transformed not only performance but psychology. Airmen began to trust their machines as extensions of themselves. They learned to ride the sound of exhaust-driven power through the worst skies on Earth. When the U.S. Army Air Forces compiled its final European statistics, one figure stood out: over 1.4 million tons of bombs dropped from turbocharged aircraft. It was, in many ways, a testament to the principle that power could be reclaimed from waste, that technology, properly applied, could reshape the tempo of war. But victory brought new questions. As jet propulsion loomed on the horizon, engineers wondered whether the turbosupercharger was merely a stepping stone, or the last triumph of piston-driven flight. The answer would emerge not in Europe, but over the Pacific, where altitude once again became a battlefield. In the Pacific, the turbosupercharger's legacy took on a new form, one of endurance, distance, and vengeance. The sprawling distances from island to island demanded aircraft that could climb high, fly far, and carry more than any plane before them. It was here that the B-29 Superfortress entered the story, a machine built around the lessons learned from the B-17 and its turbocharged ancestors. Each of its four Wright R-1820 duplex cyclone engines was fitted with a General Electric turbosupercharger, the most advanced version ever built. Together, they produced over 8,000 total horsepower, enabling the B-29 to operate at 31,000 feet, while carrying nearly 20,000 pounds of bombs. This combination of altitude and payload was previously unimaginable, and it gave the United States an entirely new strategic reach. Japanese observers on the ground were stunned. Their anti-aircraft guns, designed for medium-altitude raids, fell short. Their interceptors climbed desperately but began to stall long before they reached the silver giants gliding above the clouds. One Japanese officer later wrote, "They came from the sun, too high to fight, too fast to follow." The turbosupercharger had effectively ended Japan's defensive advantage. Where German cities had burned under precision raids, Japan faced devastation on a scale no one had foreseen. From the firestorms of Tokyo to the final missions over Hiroshima and Nagasaki, the high-altitude bombers were now instruments of both engineering mastery and moral reckoning. But within American command circles, the technology was viewed not as a weapon of cruelty, but as the ultimate demonstration of industrial synergy. Every B-29 that took off was a flying assembly of over 60,000 individual parts, produced by dozens of U.S. factories, from Michigan to Massachusetts. General Electric's turbo division alone employed more than 15,000 workers, many of them women who had never set foot in a machine shop before the war. Their hands built the scroll housings, impeller wheels, and heat-resistant alloys that made it all possible. When the war ended, the engineers who had once battled skepticism found themselves celebrated. General Electric published internal memos calling the turbo one of the decisive factors in the air victory. U.S. Army Air Forces reports praised its ability to sustain rated horsepower to altitudes previously unreachable. Even captured German scientists expressed grudging admiration. One Luftwaffe technician examining a downed P-47 engine remarked, "This is not just power, this is art." The turbosupercharger did not vanish with peace. Its principles became the foundation for post-war jet engine compressors, influencing designs like the GJ-47 that would power early Cold War fighters. The idea that exhaust energy could be recycled for propulsion would eventually shape every form of modern turbine technology. By the time the war ended in 1945, the turbo had proven something far greater than its inventors imagined: that ingenuity could overcome altitude, and persistence could transform rejection into revolution. And yet, for those who flew behind its howl, the memory remained deeply human. The echo of a device that carried them through ice, fire, and fear, toward victory at the very edge of the sky. In the end, the story of the turbosupercharger is not merely one of machinery but of transformation. It began as a dismissed experiment, a rejected idea gathering dust in a corner of General Electric's lab. Yet from that forgotten design emerged one of the most decisive engineering triumphs of the 20th century. It changed not just how aircraft flew, but what nations believed was possible. The United States had proven that innovation could conquer nature itself, that altitude, distance, and speed were not limits, only challenges waiting to be solved. For every engineer who filed blueprints under flickering fluorescent lights, and every mechanic who tightened bolts in freezing hangars, the turbo's whisper became the sound of progress. In Europe, it allowed the Allies to strike at the heart of an industrial empire. In the Pacific, it lifted bombers so high that the world itself seemed to fall away beneath them. And in the years that followed, its principles would ignite the jet age, the space age, and eventually the digital revolution, each built on the same idea of harnessing the invisible, the wasted, the unseen. For the men who flew those missions, the memory of that deep metallic hum remained long after the war. It was the sound of trust, of an invention that refused to quit when oxygen thinned and engines screamed. And perhaps that's why it still resonates in the history of American innovation. Because from rejection came resilience, and from exhaust came the power to lift a nation above the clouds.